Good morning, good afternoon, good evening, wherever you are. Welcome to the stream today. Today we have Anahit joining us, and she's going to chat with us about the art of embracing failures in serverless. So let me bring up Anahit. Hey, how are you doing?
I'm great. How are you doing?
Pretty good. Yeah, just getting started.
Early morning for you.
Yeah, end of the evening for you. So
yeah. End of the workday at least, so that's positive.
Yeah, definitely. Awesome. Let me get your slides up here. Cool. Right. I can leave you to it.
Wonderful. So imagine that you have built this simple serverless architecture in the cloud. You have picked the services you want to use, you connect them together, and everything just works like magic because, well, that's what serverless is, right? So much so that you decide to go to production with it, and all of a sudden hell breaks loose and everything starts to fail in all possible ways, shapes, and forms. And there's nothing you have done wrong, at least that's what you think, except for maybe not reading all the extensive documentation of all the components and all the libraries that you are using. But well, let's face it, who does that nowadays anyway, right? So what's the next logical step? Maybe you just swear off using the services or architecture in question ever again because, well, it just doesn't work. And what's wrong with the cloud anyway? Why doesn't it work? And serverless is probably just an expensive fad. Let's just all go back on-prem and use good old monoliths, right? So purely statistically speaking, we should probably consider that the problem is not necessarily the cloud or the cloud provider, maybe not even the services or the architecture that you picked. So what is it then? As Murphy's Law says, anything that can go wrong will go wrong, though I personally prefer the more extensive version of it that says anything that can go wrong will go wrong at the worst possible time. And my name is Anahit, and I'm a lead cloud software engineer at a company called Solita. I'm personally based in Finland, and I'm also an AWS data hero. And there's this funny thing I noticed after becoming an AWS hero. People started to come to me with this smirk on their faces and asking, so tell us now, what's wrong with the cloud? Why doesn't it just work? So I'm finally going to answer that today. Or maybe not exactly that, but I want us to look together at something that we as humans don't usually feel comfortable looking at: failures. And I hope that this talk helps you to become a bit more aware and curious, to maybe spot patterns that others don't necessarily see, and to have the tools to ask questions and make conscious and critical decisions, taking control into your own hands rather than believing in magic, and become a little bit paranoid, but in a good way. Because to borrow words of Martin Gladman, in distributed systems, suspicion, pessimism, and paranoia pay off. But before we start talking about the distributed systems and failures any further, let's briefly go back to our story with this failing serverless architecture. There's actually a prequel to it. So once upon a time, you were just a developer who started developing software that was probably supposed to run on a single machine somewhere in an on-prem data center. And the only thing you actually cared about were the so-called functional requirements, so that your code does what it's supposed to and has as little bugs and failures as humanly possible. That was your definition of reliability. And there could, of course, have been some occasional hardware failures, but usually you didn't care much about those things. Were mostly deterministic. Everything either worked or, well, it didn't. Next thing you know, you find yourself in the cloud, maybe using virtual machines, and all of a sudden you start developing software that requires you to think about the so-called non-functional requirements. So things like certain levels of availability and scalability. Also, reliability and resilience suddenly get a whole new meaning, and you still need to take care of those functional requirements and make sure that, well, the code works and has as little bugs as possible. But the complexity level just went up a notch, and you need to care about so much more. And also, failures are starting to become a bit more pronounced and a bit less deterministic. Welcome to the dark side, the wonderful world of distributed systems, where with great power comes great responsibility. But things didn't stop there, and before we know it, you jump over to the serverless side. And everything seems to be simple again. You just pick the services, you connect them together, and everything works like magic. You don't really see any machines around. Moreover, the word serverless suggests that you don't really need to be looking for any machines. And the cloud provider takes care of those major utilities for you, things like availability, scalability, reliability. And you're once again back to just making sure that your own code works and does what it's supposed to and not caring about anything else. Only we kind of know that that's not exactly how our story went. Because, well, anything that can go wrong will go wrong. So what exactly can go wrong? To set the stage, let's look at serverless, distributed systems, cloud in really simplified terms. So distributed systems is simply a bunch of machines connected by a network. And while it provides a lot of new and exciting ways to build solutions and solve problems, it also provides a lot of new and exciting ways for things to go wrong. Because resources you are using are no longer limited to just a single server, single machine. They are distributed across multiple servers, server racks, data centers, maybe even geolocations. And well, instead of just one machine that can fail, we now have plenty. And those failures can happen really on any level. It can be software failure or hardware failure, maybe operating system, CPU, memory, hard drive, you name it. And all of those failures can happen completely independently of each other in a most non-deterministic way possible. But the worst thing is that all of those machines are talking to each other over a network. And network is known for one thing in particular. Whenever any communication is happening over the network, it will eventually fail. Now, any cloud is basically built on top of such distributed systems. That's where the superpowers come from. And the cloud provider takes care of the most difficult part of managing the underlying distributed infrastructure, abstracting away that low-level complexity away from us, and giving us access to this shared pool of resources, such as compute, storage, network, doing that at a truly massive scale. And that scale, no individual user can ever achieve that scale, but especially on the bigger scale. If something has a tiny little chance of happening, it most certainly will. And serverless and managed services, wherever that fuzzy line goes nowadays, are a step up in this abstraction ladder. They make the underlying distributed system seem almost invisible, almost magical, so much so that you might even forget it's there. But by using serverless and fully managed services, we didn't just magically teleport to a different reality. We are still living in the very same messy physical world. And we are still using the very same underlying infrastructure with all its built-in complexity. And this higher level of abstraction certainly makes a lot of things easier, just like a higher level programming language would. But it also comes with a danger. Being seemingly simple to use, it might give us this false sense of security. And that in turn might make spotting potential failures that much harder because they are also abstracting away from us. And the reality is failures did not go anywhere. They are still there embedded in the distributed systems waiting to show up. And as Leslie Lampert said already in 1987, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And we could really rephrase it for serverless. A serverless architecture is one in which a failure of a computer you had no idea existed can render your own architecture unusable. But with serverless, rather than seeing these hardware failures and things like blue screens, we see failures manifest in a bit different, sometimes less obvious way. Now, let's climb one last step in our abstraction ladder, and let's focus on building distributed applications on top of serverless and managed services. So in essence, what we do is we split the problem at hand into smaller pieces. We pick services and resources for each of them, and then we connect all of them with things like events, messages, HTTP requests, and all of them are using network in some shape or form. So in essence, a distributed application mirrors the underlying distributed system. It also gives us this great power to build applications in a completely different way. But just like with the underlying distributed system, the architecture we are building is susceptible to very similar trade-offs. It is likely going to be complex. Every piece can fail at any given moment, the most non-deterministic way. And whenever there is any communication happening over network, it will eventually fail. Now, there's a special type of these distributed applications, which are called data applications. And with data applications, we basically focus on collecting, storing, and processing large volumes of data. And the data itself can be anything that you have, maybe log data, IoT, website clickstreams, whatever data you have in big volumes. And on one hand, that large volume of data makes it somewhat easier to spot potential failures, because at big scale, if something has a chance of happening, it most certainly will. But on the other hand, failures in data applications are typically not as obvious as the ones in, let's say, client-facing applications. And quite often, if there is a failure when processing the incoming data, no one will probably resend you that data. Once the data is lost, it's lost forever. So how do we make our distributed applications more resilient in the face of all those impending failures? Well, we are mirroring the underlying distributed system. Let's take a look at how the cloud providers are dealing with all those failures in distributed systems. After all, they do have quite some experience with that. And of course, there's a lot of complex algorithms and mechanisms at play when it comes to building resilient distributed applications or distributed systems. But surprisingly, the two of the most essential tools for making distributed systems more resilient are also seemingly simple. They are timeouts and retries. And those are the things that we absolutely need to be aware of when we are building our distributed applications. I call them these hidden superpowers, because while they can be extremely powerful, we also need to be very careful and mindful how we use them. And we will see soon what I mean. So you might have noticed that so far I haven't even mentioned any specific cloud provider or any specific service, because those are the things that are pretty much universal to all of them. But now it's finally time to move on from our fictional story. And actually, it's time for me to confess that the story wasn't probably as fictional as I wanted you to think. In fact, this is something that happened to me to some extent. So I was working with a customer who were building this simple yet powerful distributed architecture for near real-time data streaming at a pretty large scale. On a quiet day, we would get over 0.5 terabyte of data. And we had a producer that received that data that we wanted to store, collect, and process. And for that, we took Kinesis data stream. We connected it to our producer application. And on the other end, we connected an AWS Lambda to it. And just like that, we just built ourselves a powerful data processing pipeline. And everything was great, really, until one day we realized that we were actually losing data, and we didn't even know it was happening. Thank you, this higher level of abstraction, I guess. So what exactly was going on there? Let's go step by step. First of all, what is Kinesis Data Stream? So it's a fully managed and massively scalable service to stream data on AWS. After you write the data to the stream, it is available for you to read in milliseconds, and it's stored in a stream for at least 24 hours, but you can configure it to be up to a year. And during that entire time, you can consume or replay, as they say, that data as many times as you want. But whatever you do, you cannot delete the data from the stream. So once it gets to the stream, it stays in the stream for at least 24 hours. So Kinesis is actually a very powerful tool for a great variety of applications, and there's no need to manage or scale any clusters or servers, and it comes with massive scalability. To achieve that massive scalability, Kinesis uses a concept of a shard, which is probably familiar to many, but in the context of Kinesis, you might think of a shard as just an ordered queue. And each stream will be composed of multiple such queues or shards. And each shard will come with capacity limitation. You can write up to 1 megabyte or 1,000 records of incoming data per second. But the number of shards you can have in your stream is virtually unlimited. So you can add as many shards as you want to stream as much data as you need. And to get all that data to Kinesis, we have a choice of 2 different API calls. We can either write individual records to the stream, or we can batch up to 500 records and send them in single put records batch API call. And batching in general is much more efficient and less resource intensive way for making API calls, especially if we are dealing with those data intensive applications where we can have a really huge number of individual API calls. In that case, batching is very helpful. But once again, if something seems too good to be true. There usually is a catch, and we'll get to that catch in a moment. So we have established by now that failures in distributed systems and architectures are pretty much inevitable, especially at the bigger scale. So how do those failures manifest at this higher level of abstraction with services like Kinesis, for example? Well, turns out it's pretty straightforward. When we interact with the servers, with the services from our code, we are using API calls. And each that API call can fail at any moment. So the good news here is that if you're using AWS SDK to make those API calls from your code, the SDK will take care of most of those failures for you. After all, AWS knows firsthand that the failure will happen. So they have built into the SDK one of those essential tools for better resilience, or a superpower as we know it now, the retries. Now, the trouble with the retries in general is that we have a potential to turn these localized intermittent problems, like a network glitch, for example, into a truly massive one. Because retries can have an unexpected blast radius. They can cause this ripple effect of cascading failures through the system, and we can ultimately bring the entire system down with our retries. Because retries are inherently selfish. It's just like when you're pressing that refresh button on the browser when page doesn't load. We all know we shouldn't do that, but we all do that anyways. And retries imply that our request is more valuable and more important than anybody's else. And we are ready to consume resources, to add load and potential costs to the downstream system, just making sure that our own request goes through no matter what. But retries are not even always effective, neither are they safe. So first and foremost, where do we even retry? In what cases do we want to retry? Let's say a downstream system like an API or a database is already under a heavy load, and that's what is causing the failure in the first place. In that case, well, retrying will probably only make the things worse. Or let's say that our original request timed out, but we are not ready to wait more time than, or we are not ready to wait the time it will take the retry to complete. For example, we have our own SLA requirements. Well, then retrying is pure selfish in that case, because we have wasted resources for nothing, just like pressing refresh button and just closing the web page. And what if the downstream system has their own retries implemented? Let's say they also have this distributed architecture and they have retries on several levels. Well, then our retries will just multiply and amplify all the possible issues that can happen, and they will become even more dangerous. And that's where we actually see this ripple effect of cascading failures, especially if we start retrying right away without giving the underlying system any time to recover. And so what if the operation that we are retrying actually has some side effects? Let's say we are doing some database updates. Then retrying can just cause unpredictable results. So there are many different considerations, but the bottom line is we need to be very mindful about how we use this superpower. Luckily, in the case of AWS SDK, it comes with these built-in safety measures. So if a request to a service like Kinesis, for example, fails for some reason, SDK will only retry or only handle the so-called retryable failures. So things like service unavailable, other 500 errors, or timeouts. And for those retryable errors, it will retry the failed request on your behalf behind the scenes, but it will stop after a certain amount of attempts. And between those attempts, it will use the so-called exponential backoff. And this is done, or this basically means that the delay between retry attempts is increasing exponentially. And those are seemingly simple but crucial details that can either make it or break it. They actually can turn retries from being a very powerful tool for better resilience to the main cause of system outages. Because we only want to retry when it can actually help the situation, so only transient errors. And we don't want, or if we do retry, we want to limit the retry attempts and stop retrying when it doesn't improve the situation anymore, to reduce the chance of cascading failures down the stream. And we want to spread the retry attempts as evenly and uniformly as possible, instead of just sending these bursts of retries right away to overwhelm the system that is probably already under a lot of stress. And with AWS SDK, you have these safety measures built in, but sorry, technical problems. You have these safety measures built in, but also the ability to configure those retry parameters. And here you can see the example how you would do that with JavaScript SDK. And every language will certainly have their own ways to configure and own default values, but all of them will allow you to configure some of those parameters. And the same way, they will allow you to configure this other superpower or timeout related values. And if you think now that timeouts are not really a big deal and they don't sound too much like a superpower, well, I encourage you to think again, because, well, in distributed systems, timeouts are pretty much a given. So let's once again take a brief glance under the hood in very simplified terms. So when we interact with the serverless or any other service from our code, we are just using API calls abstracted away as SDK method calls. And they look exactly the same as any other local method invocation would. But let's not let that fool us, because we know that the network is still there. It's just abstracted away from us. And every request sent over the network, just like API calls to Kinesis, can fail in various different shapes and forms. Moreover, it's usually almost impossible to tell if the request actually went through or it didn't, because failures can happen on many different levels. Maybe sending the request failed, or maybe actually processing the request failed, or maybe the service is busy and the request is just waiting in the queue to be processed. Or maybe it was processed, but you just never received the response back. So you don't know. In any case, there's so many different options, but the end result is the same. You might be stuck waiting for something that will never happen. And this can happen to any service, no matter how serverless or not it is. And not to wait forever, AWS has built into the SDK this other tool for better resilience, the timeouts. And the ability to configure those timeouts for API calls is this other hidden superpower that we have. And just like with the retries, we need to be extremely careful about how we use it. Because picking the right timeout value turns out to be a very difficult task. And just like any decision in our architecture, it will come with certain trade-offs. Let's say you pick too long timeout values. Well, they can be ineffective, and they can also increase the load and latencies and consume resources. Too short timeout could cause some retrying too early, which means you don't give the original request a chance to complete before you start retrying. And this in turn will inevitably increase the load on the underlying system even more, and ultimately cause that familiar ripple effect of cascading failures. And on top of that, of course, appropriate timeout value will be different for every single service or every single operation, or every single operation that you're trying to perform. Now, for the longest time, I have been scaring people by telling that in spite of all that, AWS SDK, JavaScript SDK, will wait for 2 entire minutes for any request to time out. So it takes 2 minutes for the SDK to decide that it needs to time out the request. And this was universal across all the services. And if you think about it, 2 minutes is a horribly long time, especially if we are dealing with these low latency systems like Kinesis or let's say DynamoDB. And here we are just waiting for 2 minutes for the SDK to decide to time out our request and to retry it. Well, things have changed ever since. So the JavaScript SDK has luckily been updated from version 2 to version 3. And there have also been some updates to the default timeouts and everything related to how timeouts are handled. Well, the default timeouts are now infinite. Congratulations. So either be prepared to be stuck forever waiting for something that will never happen, or better so, configure the appropriate timeout values. This is extremely important. Now, here we finally get to the first reason for losing data in our fictional, not so fictional story. So not configuring proper timeouts just blindly going with the defaults and waiting for too long can exhaust the resources of the producer and make it not being able to process the new incoming requests, and hence we will end up losing data. And that's, of course, exactly what we were seeing. So, and that was even before that infinite timeout era. It was still at the time of 2-minute timeouts. And still we managed to overload our producer application and make it not being able to process data. So because of likely a temporary fault in network or service, we suddenly had a complete system outage at our hands, which, if you think about it, is a complete opposite of what a resilient system should be, because we want to mask individual failures. We don't want to amplify them. Now, this obviously doesn't sound too great, but if you think the solution is to have short timeouts, I must say that short timeouts are not safe at all, neither. In fact, I would say that short timeouts might be even more dangerous than too long timeouts, especially if they are combined with the retries. Because again, retrying the request before it had the chance to actually finish will inevitably increase the load on the downstream system. And this can cause all sorts of fun things like increased latencies, increased costs, of course, increased amount of errors. And this can ultimately cause this ripple effect of cascading failures, and once again, ultimately bring the entire system down and cause a system outage. And if our goal is to build a resilient system, which probably it should be, we need to mask and recover from individual failures. We don't want to amplify them. We want to ensure that the system functions as a whole in spite of those individual errors. And here's where this wrongly configured timeouts and retries can become a real match made in hell. So once again, even though retries and timeouts can be extremely powerful, we call them the superpowers, we need to be extremely mindful about them. We don't want to just blindly go with the defaults, because defaults can be incredibly dangerous. So when you get back to your own code, just please go ahead and check all the default timeouts for all the requests that go over network, maybe SDK calls, or maybe you have some external API calls. Please make sure that you know what the timeouts are and you have control over them and configure them appropriately, because you need to take control into your own hands. The defaults can be very dangerous. And especially if those timeouts are combined with the retries. Now, this far, I have been talking about those inevitable failures that are innate to distributed systems in general. But there are also these special kinds of failures, which are caused by the cloud providers on purpose. And those are the failures that are related to service limits and throttling. And in case of serverless, this can be particularly confusing, because when we are promised scalability, which we are with serverless, we somehow tend to assume infinite scalability. But if something seems too good to be true, it's probably just that, because of course, no resource is infinite, and sooner or later, we need to face the reality. And the reality is, cloud is not infinite, and we don't need, or we don't have the entire cloud at our own disposal. We are sharing the underlying resources with everybody else. And sharing those resources naturally comes with some trade-offs. On one hand, we do have this massive pool of capacity that we can share. But on the other hand, it might also mean that there can be individual users that can either intentionally or unintentionally try to monopolize the resources. And while resources are not infinite, it will inevitably cause this service degradation for everybody else. So service limits are there to ensure that this doesn't happen. And throttling is basically just a tool to ensure those, or to enforce those service limits. And for example, in case of Kinesis, we had this shard throughput limit of 1 megabyte or 1,000 records per second. And whenever we reach that limit, all the other requests will throttle. They will fail. And this brings us to the next reason for losing data in our story, because there was definitely more than one reason. So I said a while ago that AWS SDK will handle most of the failures for us, right? But of course, there's a catch, because in case of batch operations, like we have these put records here, instead of just handling the failures of the entire request, we should also handle the so-called partial failures. Now, the thing is that those batch operations, they are not atomic. They are not either all succeeds or all fails. Part of your batch might go through and the other part might fail, and you would still get a 200 success response back. Moreover, every single record in that batch might fail, but you still get a success response overall. So it's your responsibility to detect those failures, and it's your responsibility to handle them yourself. Otherwise, you just don't know that they are happening. And the main reason for that kind of failures is exceeding one of the service limits or throttling. So luckily, we already know that there is this special superpower that can help us with transient errors, and exceeding service limits because of some occasional spikes in traffic is certainly a transient error. And those are the retries. And when implementing this partial failure retries, or any retries for that matter, we should look at the 3 key things that we need to remember. So let's go through them one more time. We only want to retry if it can actually help transient failures. We want to set the upper limit for the number of retries. We want to stop retrying if it doesn't improve anything. And we want to use proper backoff between retry attempts, not to overwhelm the system that is probably already under a lot of stress, because we are likely already seeing throttling. So we are already exceeding service limits. We don't want to push it even further. And for that, exponential backoff and jitter are actually a very simple tool how we can handle those backoffs or use proper backoffs. So I didn't mention it when I talked about SDK, but this is exactly what AWS SDK uses itself. So the jitter is just a randomization that you add to the exponential backoff. This is an extremely simple tool that allows you to improve the results of your retries dramatically. There have actually been studies that would show that properly defined jitter can actually improve it by number of magnitude, if I remember correctly. But this is a very simple tool that will allow you to decrease the number of retries that you need and to increase the chance of your request to go through. So I always say that if you remember anything from what I say, let it be timeouts, partial failures, and retries with exponential backoff and jitter. Those are extremely important things when you are dealing with any distributed application, and they can save you a lot of headache in the future. To borrow words of Gregor Hoppe, retries have brought more distributed systems down than all the other causes together. Of course, this doesn't mean that we shouldn't retry, but again, we should be extremely mindful about how we do it. We don't want to kill the system that we are actually trying to fix. Speaking of which, let's see what happens if we, again, let the error handling slide go with the defaults on the other end of our architecture. And it turns out things can escalate pretty quickly here as well. So if you remember, I had a Lambda function acting as a stream consumer. So let's go into that and see what happens there. So Lambda itself is really a prime representative of distributed architectures because it consists of many hidden components that work together behind the scenes and make Lambda so very powerful. And one such essential component, my personal favorite, is called the event source mapping. And it's very well hidden underneath Lambda abstraction. If you haven't heard about it before, don't worry, many haven't. And it is really very important, especially when working with streaming event sources, because when you are attaching a Lambda function to Kinesis stream, for example, you're in fact attaching an event source mapping to that stream and then pointing your Lambda function to that event source mapping. And it will be the event source mapping that actually picks the records from the stream, it batches them together, and it invokes your Lambda function code for you. And those records will be picked from all the shards in the stream in parallel. And you can configure to have up to 10 Lambdas reading from each shard in the stream at all times, which would basically mean that you can have up to 10 times as many concurrent Lambdas reading from the stream as there are shards in the stream. And here's where the true power of concurrent processing kicks in, because you're now able to parallelize processing of the records. You can speed things up. And as usual, when something is really powerful, there are things that we need to be aware of. And by now we know that nothing is infinite and nothing scales infinitely, not even Lambda. And here is where we can very easily hit this extremely important limit for Lambda called Lambda concurrency limit. And this particular limit basically means that you can have a limited number of lambdas running concurrently in the same account, the same region. And by default, it's 1,000, or nowadays I've heard it's around 100. But whatever it is a soft limit. You can increase that by submitting a support ticket. But whatever the increase will be, there still is going to be a limit. And once you hit that limit, all the new Lambda invocations in that account, in that region, will be throttled. They will fail. So imagine you have a Kinesis stream with, let's say, 100 shards, and then you set the parallelization factor in the event source mapping to be 10. And this gives you 1,000 lambdas just reading from the stream at all times. And things will probably be okay until there is some other lambda somewhere in that account in the region, probably doing something extremely important that has absolutely nothing to do with your Kinesis stream, and that lambda starts to fail because your stream consumer has consumed the entire capacity limit or concurrency limit for lambda in that account, in that region. So what I'm saying is that this is a limit that can have an extremely big blast radius. It can actually cause this ripple effect of cascading failures that go way beyond your own system and architecture. So you need to be extremely mindful about this. But getting back to reading the records from the stream with Lambda. So what happens if there's a failure while reading the records? Now, once again, it's a good news, bad news situation. The good news here is that wonderful event source mapping comes with this extensive set of error handling capabilities. But to use them, you actually need to know where to look. So the chances are pretty high, and that's the bad news, the chances are pretty high you will blindly end up going with the defaults. And by now we should know that defaults are really dangerous. So what happens by default if Lambda fails to process a batch of records? For example, there was some bad record with some corrupt data, and we just let it slide. We didn't implement proper error handling in the code because, well, nothing ever can go wrong. And anyhow, our Lambda fails because of that bad record. So what happens next? Even though in this case, no amount of retries can really improve anything because, well, there's just a bad record in the batch, but by default, Lambda will try to reprocess that batch of records over and over and over again until it either succeeds or until the data in the batch expires. And in case of Kinesis, well, data expires in at least 24 hours. So this basically means that Lambda will be retrying completely unsuccessfully that one batch of records for 24 hours. And you probably can imagine the number of useless Lambda invocations that come with us. And mind you, they are not free at all. And to add to that, those useless retries will likely cause reprocessing of the same records. Because you see, from the perspective of the event source mapping, either the entire batch succeeds or the entire batch fails, which means that if Lambda throws an error, it doesn't care that some of the records in the batch might have already been processed. It will reprocess the entire batch all over again. Like here on this picture, if the record number 4 threw an error, records number 1, 2, and 3 will be reprocessed over and over and over again for 24 hours. That's pretty bad, but bad things, of course, don't stop there, because while Lambda keeps retrying that unfortunate batch that will never succeed, no other batches are being read from that shard. So all the other shards in the stream continue on with their lives, but that one particular batch is stuck because of that one bad record. So this means that because of one bad record, we are now facing almost a system outage, let's put it so. And that's why this kind of a bad record is often referred to as a poison pill record. And one problem here is that in data applications, data usually loses its value pretty quickly. So let's say a 24-hour-old data can be completely useless. So even though, in fact, you are maybe not dropping the records, but if you haven't processed them quickly enough, you might as well. And the way that Lambda works is not really a bug or, I don't know, some evil magic. The thing is that Kinesis promises you ordering on the shard level. So this means that the records should be read in the same order as they were written to the stream or to the shard. And if Lambda, let's say, starts to like jump over failures and retry them in the background, well, then we can't guarantee any order. The order will be lost. but even though it's a logical way of working, it doesn't make the situation too pleasant anyway. So what happens? 24 hours goes by and data hopefully finally expires from the stream. The poison pill, it has left the stream, also with the batch that is probably partially unprocessed, but what should we do? At least Lambda can continue with the stream and catch up and continue reading the data from the stream. But the problem here is that it's quite likely that your shard is filled with records that were written around the same time that your already expired batch, which means that they expire around the same time as the expired batch, which means that in the end of the day, Lambda might not even have enough time to catch up with that shard, and records will just keep expiring and expiring from the stream before Lambda has a chance to read them. So I often bring this overflowing sink analogy. When you can't drain the sink fast enough, the water just keeps overflowing. So again, we started with just one bad record, but we might end up losing a lot of valid and valuable data. And once again, it's opposite of what a resilient system should be. And of course, this is exactly what we saw in our story. So just like with poorly configured timeouts and retries earlier with the producer part, we turned a really small localized failure, one corrupt record, into a full-blown outage. And we ended up losing data, causing duplicates, causing retries, causing delays, consuming resources, increasing costs for that matter, and ultimately leading absolutely nowhere. And all of that basically because we didn't know any better and just blindly went with the defaults when it comes to the good old failures and retries and error handling. And here, once again, I need to bring up the quote by Gregor. Luckily, there are several ways in which we can be much smarter about retries with Lambda. And here, the event source mapping comes at rescue. And we can, first and foremost, configure all these useful error handling settings that we have with the event source mapping. And by now, we should know that the most important things that we should set are the retry limits and the timeouts. And we can do both with the event source mapping, but both of them are set to -1 by default, which means no limits. So here we go. And there are, of course, more extremely useful settings for error handling. I'm not going to go through them today, but knowing that they are there can save you a lot of trouble. And they can be used in any combination that you want. Once again, just whatever you do, please don't go with the defaults. And if you want to know more about those error handling capabilities that event source mapping comes with, or more in-depth description of Kinesis and how it works with Lambda and without, you can take a look at this two-part user manual, as I call it, or 2 blog posts that I've written on the subject. All right, so we have seen today that sometimes we can actually cause more problems while trying to fix them. And this is especially true if we don't make conscious, informed, and critical decisions about handling failures. And of course, every such decision will come with trade-offs, and things like retries and timeouts can be extremely efficient when used mindfully. But if we just let the matter slide and just let go with the default, these superpowers can backfire. And instead of making our architectures and systems more resilient, they can actually achieve the exact opposite. So next time you are building a distributed architecture, I encourage you to be brave, to face the messy reality of the real world, to take control into your own hands rather than believing in magic, because there's no magic. And that's a good thing. That means that we have control. We can do something about it. And distributed systems and architectures are very powerful, but they are complex, which doesn't make them neither inherently good nor bad. And the cloud, and especially serverless, takes away a lot of that complexity. It abstracts it away from us. But this doesn't mean that complexity is not there anymore, which again doesn't make them neither inherently good nor bad. And while it's absolutely impossible to know every single detail about every single service we are using, it's really madness. But there are things that are inherent to distributed systems and the cloud in general. So things like service limits, partial failures, timeouts, retries, backoffs, those are all the fundamental things that we absolutely need to understand. Because otherwise we are just moving in the dark with our eyes closed and somehow hoping that everything is going to be fine. And finally, on a more philosophical note, though distributed systems and architectures are hard, they can also teach us a very important skill to embrace the chaos of the real world. Because each failure is an opportunity to make our own architectures even better, even more resilient. And though, of course, despite our best effort, it's impossible to build something that absolutely never fails. But there's one thing that we can do. We can learn and grow from each individual failure. And as Dr. Werner Wackels likes to remind us, everything fails all the time. That's just the reality of things. So either in life in general or with AWS services in particular, I would argue that the best thing that we can do is to stay calm and be prepared when those failures happen. And that's it from me for today. Thank you.
Cool. Yeah, thanks so much for sharing with us, Anahit. I love this topic.
Thank you. Thank you very much. Yeah, somehow it's something that doesn't maybe come as a first topic for people starting to work with serverless, and many get surprised in a negative way. So yeah, I'm trying to raise awareness,
Yeah, definitely. It's like they try to be helpful with the defaults, but yeah, I've definitely been bitten by too long of a timeout, then things fail in the background. Ugh.
Yeah, right. And it's kind of, it happens everywhere all the time. And really, especially as I was saying, with anything that goes over the network, it sooner or later the request will time out. And if you don't know what the default value is, and if you have retries built on top of that, then well, it's just a recipe for disaster, really.
Right. Does anyone in the chat have any questions for Anahit or?
Hey, Jeremy.
Yeah, we got Jeremy in the chat.
Hey. Appreciate it. Right back at you. You might have noticed that I had my own individual failure in the process. My lamp just fell off the monitor.
Oh, no. Just got to be ready for them.
Yeah. Speaking of failures, was very appropriate.
All right. I guess we don't have any questions. I guess I'll do my usual spiel of, if you're joining us from YouTube or Twitch or something like that, and you want to be more involved in the Believe in Serverless community, we're mostly in Discord. So if you go to believeinserverless.com/community, that'll take you straight to a Discord invite. We invite, if you've been doing serverless for a long time, like myself and Anahit, but if you're just curious about learning about serverless, we have people from like all spectrum. So everyone's welcome. Trying to think if there's anything else. Oh yeah. It's like 6 a.m. for me. The brain fog here.
You're very brave.
We've got another stream later today, 11 a.m. Pacific time with Carlo. He's going to be talking about on outages, stories from a career in operations. So if you haven't noticed, we've got a little bit of an unintentional theme today. So, but
well, it's also close to real life.
Yeah, also seasonally appropriate too, right? Because Halloween, assuming we celebrate. So,
yep. Well, even if not, I mean, it's the time of the year when things get gloomy and all that kind of stuff.
Oh yeah, same over here. All right, I guess we don't have any questions. Thanks so much for joining. I'm going to end the stream.
Thank you.
Bye, y'all.